Hi everyone, this is Jessica Marie Emartizo from BS Electronics Engineering 3A, and this is ECE 23 Performance number 8, and now we are going to talk about entropy. So before we do that, this is what we need to know. We need to know and to compute for the entropy using Shannon's entropy equation and also the summary. So before we start, and I'm going to talk about a small background about entropy. So entropy quantifies the amount of uncertainty involved in the value of a random variable or the outcome of a random process. It is not another term is uncertainty or disorder or randomness. So entropy also can be interpreted as the total amount of information over the total number of messages. So Shannon defined the entropy as H or Greek letter eta. So H is equals to log sub 2 M. So M also means all outcomes have equal probability or upper bound of entropy. So now we are going to perform the task number 8 wherein to demonstrate the principle of information theory by determining the entropy in sending a message by using Shannon's and Hartley equations. So we are going to create a discussion on how to compute the entropy using Shannon's entropy equation. We are going to use my first name as Jessica and surname Lortizo, and we are going to arrange it alphabetically. So here it is. Right, C. So my binary machine or main letter is A, C, E, H, I, K, L, O, R, S, T, and Z. So here we go. In this one, we're in the legend here, if the circle is in the right, or let's say when you see this video, it is on the left, then it is equals to 1. And if it's in the left, or if you see this video, it is going to your right, then it is equal to 0. So ACE is equals to, then A with a question mark is equals to 1 there, and the A without question mark is also to 1 there, as you can see in this one. But I'm not going to discuss this diagram. I'm going to discuss the probabilities and also the number of bits. And here, so the binary machine number 1, we are going to discuss two binary machine, the binary machine number 1 and binary machine number 2. There you go. So the probabilities in letter A is 0.125, the same with I, K, T, Z. So, and also H. All in all, we have 0.125 or 3 bits, wherein the number of bits is 111. So how did we get that? Here, so I get it using the formula log sub 2, then multiply it. Oh no, wait. I use it doing 2 raised to negative n, wherein n is the number of bits. So A is equals to 3 bits, 111, then 2 raised to number of bits equals 3 is equals to 0.125. So that's how we get it. And also in the other letters, then in letter C, in other one, there's 3 times 0.0625 times equals to 4 bits. But we are going to discuss the probability first. So A is equals to 0.125, C is equal to 0.0625, E is the same with letter C, then H, I, K, T, Z is the same with A, then C, E, L is the same as equals to 0.0625, and also the O, R, S is equals to 0.03125. Then here we go. Then the entropy of that is 3.46875 bits. And also this is how we get our entropy here. And it is also equals to H times 3.46875 bits. Now, for the second one, here in the binary machine number 2, as you can see, this is how I arrange my binary machine number 2, wherein as you can see in the mode in the right one, in the one side, in binary bit number 1 side, I put A, C, E, H, I, K, L, and the remaining S, T, Z, S, R, S, T, Z is on the 0 side. As you can see that here. Then we are going to talk about the probability and the number of bits of binary machine number 2. Here you go. So the probabilities is A is equal to 0.25, and it is the same with letter Z. Then C O R is equals to 0.0625. Then E is equal to 0.03125. Then H is equal to 0.015626. And I and K is the same, and they are equal to 0.00782125. Now, in number of bits, A is equals to 11, C is equals to 101, E is equals to 10101, H is equals to 1010001, I is equals to 1010001, K is equals to 1010000, L is equals to 001, O is equals to 001, R is equals to 0000, S is equals to 011, T is equals to 000, then Z is equals to 00. That's as you can see here. Then 2 times 0.25 times 2 bits, here 2 bits. Then 3 times 0.0125 times 3 bits, plus 2 times 0.0625 times 4 bits, plus 1 times 0.03125 times 5 bits, plus 1 times 0.05626 plus 6 times 6 bits, plus 2 times 0.00782125 times 7 bits is equals to, the entropy is equals to 2.984381 bits. It's the same here. So here is the summary. There you go. So the summary, this is in the machine number 1 here. And the machine number 2 here, the entropy of machine number 1 is 3.46875 bits, wherein the H max of the letter is 3.584963, N is equals to 1.03125, and the RE is equals to negative 0.03125, and it has the highest entropy, most predictable, higher probability, and least random. So you can conclude that less information needed to be transmitted to get the desired outcome. In machine number 2, the summary here it is H is equals to 2.984381 bits, then the H max is equals to 3.584963, then the N is equals to 1.062501, then the RE is equals to negative 0.062501. It has the lowest entropy, least predictable, lowest probability, most random, and it needs more information needed to be transmitted to get desired outcome. So that's all. Thank you. This is Jessica Marie M. Nartizo from BS Electronics Engineering 3A, and this is performance number 8 ECE 23. That's all. Thank you.